Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 4, Electricity and Magnetism, Inquiry Question 2, Electric Circuits. I'm going to be covering these two particular dot points. Now, the first one we have talked about in the previous slides. However, we are going to just recap on some details, particularly on the ohmic and non-ohmic components. And then we're going to apply that to energy conversions with these equations here. So that's your textbook reference that you'll be looking at. We'll be investigating the relationships between voltage and current for Ohm's Law. And we're going to try and look at factors that affect resistance in circuit and also the conversion of energy in circuits. So just to recap on what we talked about before is the concept of resistance. Now, the one thing that I didn't make clear in the previous lesson was that Ohm's law, unlike other scientific laws like the law of conservation of energy, is not a, how to put it, a fundamental law. So not everything has to follow Ohm's law. So Ohm's law is not one of the fundamental laws. For specific scenarios, it will be obeyed. For others, it won't be. And what we're going to try and explain is which ones will we see it, which ones won't we see it. So that will take us to this point here, looking at ohmic and non-ohmic resistors. And obviously looking at again in terms of the potential difference in a circuit. So what we need to look at firstly is the cause of resistance. We talked about this before, but it's to do with this fact that electrons, or the valence electrons in any atoms, are constantly drifting inside a conductor. So as an electron is moving, they will collide with any positive ions. So let's say I have positive ions here, positive ions here. They're going to collide with these ions. And in that collision, what actually happens is some of that collision is converted into heat energy. And so that's where some of that loss of energy comes from. In terms of, the drifting of these electrons, if you do put an electric field into where the conductor is, the electrons will attempt to drift towards the positive terminal, but just remember, even though they're moving in a particular direction, they're still drifting and colliding with all these different lattices or positive ions inside that metal conductor. So there are other ways that we can actually increase or decrease the resistance of something going through a wire. One of the ways of doing it is actually the length of the conductor. So the longer the conductor is, the more collisions will occur, hence we have a greater amount of resistance. So think about it this way, some people might hear the concept of collision theory. So if we're increasing the number of collisions, we're also, or maybe percentage of collisions, we're actually increasing any interactions. So that's increasing interactions, that increases energy loss, and that will also lead to a greater resistance. So that's why if you have a longer wire, you will expect to see more resistance than a shorter wire. Another way of working this out is obviously the cross-sectional area. So if we're looking at maybe a piece of wire of this particular thickness compared to maybe a really thin wire of this particular thickness, this one will have a greater resistance. The reason being, or this one will have a lower resistance, the thicker wire will have a lower resistance because the atoms inside the wire are spread out further. Okay, so that's what we're talking about there. So as we increase that, we reduce collision. So we reduce collisions, because there's more space for our charge carriers to travel through. And that's kind of the main point we're talking about here and what we're looking into. Another way that can influence resistance is the conductivity of the metal conductor or the temperature. So some materials will have stronger forces of attraction to the electrons. So a greater potential difference will have to be applied to cause the same current in the material to be held less firmly. Again, this would be the difference between an insulator and a conductor. So with a conductor, it's much lower resistance in comparison to an insulator. So we know that conductors will have free localized electrons, so it has a lower resistance in comparison to an insulator, which has a much higher resistance in that comparison. As we also said, as the particles collide with other particles, that's going to create heat energy. That also leads to higher temperatures. When we have higher temperatures, we also see that because temperature and kinetic energy are directly proportional to each other, a higher kinetic energy will lead to, or a higher temperature, sorry, will lead to high kinetic energies of the particles. So you can see that the particles, if they were just in this region here and you have your electrons coming through, if they have more or if it's a higher temperature, they're going to be vibrating a lot more. So they're going to be shifting backwards and forwards, or that kind of orientation. And there's an increased probability, because they're shifting in multiple directions, that they will collide with these charge carriers. So that's another reason why temperature might go up, and resistance. So there's that. What I want you to fill out right now is a couple of ways we can actually increase or decrease electrical resistance. So when it comes to length, if the length of the conductor is increased, then its resistance also increases, because we are increasing because we have a greater percentage of collisions that could occur. B, to maintain the current flowing through a conductor at the same level as a shorter conductor of the same material, the cross section will have to be what? So our cross section, if we want to maintain the current flow, so if we've shortened the conductor, that means we've reduced the resistance, so resistance has gone down. And so in terms of the cross section, we must also decrease our cross section in order to increase the resistance to maintain the current flow. Okay, the next one we have is the resistance of a thin conductor is higher or lower in resistance. So if it's more thin, it has a higher resistance. When the infilament, so imagine you have a light bulb, the old standard light bulb, you have a filament, so this little piece of metal wire gets hot, it's what will do what? So its resistance will increase. So as things get warmer, we should expect an increase in the resistance. Okay, we talked about this formula here of Ohm's law. We said that you can rewrite it like so. Just to recap. Now Ohm's law is stated very clearly, if it's an ohmic device, I mean by it follows Ohm's law, then when voltage increases, we should also see a increase in current. If voltage decreases, current also decreases, like so. We also try to show the relationship of Ohm's law. So voltage is the energy provided to make a current move through a circuit, and then obviously resistance, which in this case is constant, is the thing that's obstructing the flow of the electrons and other positive charges. When we say ohmic circuits, we're saying that the resistance is constant. Okay, so ohmic circuits, we have a constant resistance. Now the way we can work it out is if we do any scientific experiments, if we try and measure out the voltage, so if we try and change the voltage of a particular circuit and then measure the amount of current, and if we plot that on a little graph, we should see a straight line gradient. So obviously if we have a straight line gradient, that would imply that when we obtain the value, it is going to be a fixed value. So that value doesn't change, it is just at a flat rate in that sense. If you find any circuit or device that gives you this straight line trend, then you're dealing with an ohmic circuit there. So under all circumstances, the resistance will stay the same, obviously assuming the environment you're in also has the same conditions. So the temperature hasn't changed, you're not working in a different sort of atmospheric pressure, those kind of things there. Let's quickly do some calculations using Ohm's law. So we have 6 coulombs of charge and has a resistance of 4.5 ohms per second. What's the electric potential across the ends of our wires? So we know that Ohm's law is V IR. We know that in terms of current, it's charge divided by time. We also know what the resistance is. Alright, it's per second. So what we can do is a little cheat code, although it hasn't actually explicitly told us the time taken for this charge to move. We're assuming that it is 1 second because that's what the question tells us. So we have 1/6, so we have 6 amps of electricity flowing through. And we have a resistance of 4.5 per second. So we're accounting that for this calculation here. So what we get is 6 times 4.5, and that's our potential difference there. Okay, so following in question 3, we have a farm generator that has an output voltage of 240 volts. It's intended to operate the machinery from some distance away, so we assume that this is where our generator is. It is going to go through a cable of 5 ohms and then an operation current of 25 amps to this whatever endpoint we want to call it. The question's asking what is the potential difference across the two ends of the cable. So assuming that our particular end we're talking about, so potential difference is what we had as the final minus the initial. So the final voltage that we're dealing with is a component of the current times the resistance subtracted by the 240 volts that we used. So the overall potential difference we get here is negative 115 volts here. Now obviously in voltage it is a scalar quantity, so we can just put it into 115 volts as our potential difference. So you can see that there is a drop off in terms of the voltage from one point to another there. Okay, the next point we need to look at is non-ohmic circuits. So non-ohmic circuits is, as you can see with this graph here, it doesn't follow a straight line structure. It's sort of an exponential sort of curve going upwards. Now what that essentially means is the resistance is very small, And obviously, as you increase the voltage, that current goes really high. That overall resistance is not, constant. So where you can see that is actually in semiconductors and diodes. So this is diodes as in LED lights. So most of you at your own house should have LED lights. They're really bright, very efficient, which is also kind of the reason why we've transitioned to using LED lights over the old filament globes. What we're going to look at now is power loss and energy conversion. So how does this follow Ohm's law? The most important aspect of power loss and energy conversions is actually through transmission lines. We actually know for a fact, and this we'll talk more about in Year 12 Module 6, the longer the cable we already talked about, the greater the resistance in the wire, so there's greater energy loss here. So in Year 12 we actually talk about how we can reduce the power loss or energy loss. For this part, we're just going to look at the actual equations and then what kind of happens following Ohm's law. So we know for a fact that the power of an electric circuit is given by this formula here. So the power is, or the amount of energy that's being used is voltage times current. Okay. Now we know from Ohm's law, that we can substitute the equation in like so. Now, from what you remember when we first talked about the origins of resistance, the current, so how much interaction the charged particles have with the wire, that's the thing that will affect the overall resistance of the circuit. So if I rearrange the equation where I make I the subject of my equation, so if I substitute V away, I will get the power is equal to IR times IL here. When I times that together, it becomes I squared R. We actually call this the power loss. So it's the rate in which power can be potentially lost in a circuit. So that's how we look at that. Another way you can sort of show power and resistance is by voltage, but we do know it is the current of the circuit that will affect the overall power loss in a circuit. So just a couple of questions for you here. Firstly, it says calculate the current of these globes if it's marked with 240 volts at a power rate of 40. Remember that power, the units for it is W, which is watts, and this we've talked about before. So we know that power is equal to voltage times current. So if I rearrange the equation, or actually let's substitute our values in first. So 240 I, and so its current is just 240 like so. And if I put that to about 3 sig figs, that's about 1.67 amps there. It says calculate the resistance in their filament. So this time we're using Ohm's law. And again, what you should be doing is trying to substitute your values in first. And so we have R equals 2, our 240 volts, divided by this value here. And in 3 sig figs again, we get roughly 1,440 ohms. Question C, it says different globes, or a different globe is marked 40 watts, but its voltage reading is blurred. Its resistance is measured to be that. What is the operating voltage in this case here? Okay, so I know for fact that power is equal to voltage squared divided by R, so I can use this equation here. So if I substitute everything in again, 25, and then we have a voltage squared, so this will become V square root of 22.5 times 40 here. Just rearranging the equation there, and the value we get is 30 volts. Mind you, just wanted to remind you, this equation is not on formula sheet. This equation is, and also P equals I squared R. That's also on your formula sheet. This one is not on your formula sheet. Question D, it says, predict what would happen to this globe if it was used in a 240 volts. Yep, so a 240 volt circuit. Okay, so if we have a look, if we use 240 volts, but the operation voltage is only 30, the circuit is way larger than our actual globe. So the what we could say is the 240 volt circuit, that's too high for the operation of a 30 volt globe. And what will actually happen, this will actually cause a thing called short circuiting, and that can end up breaking our circuit. It can possibly explode, or at least explode the wires, so it wouldn't be functional. Alright, so we did talk about, in terms of transmission lines, we talk about in year 12 that the power loss in any of these transmission lines, it's caused by the interaction of these electric currents interacting with the atoms of the wires here. We are going to look at other ways to, calculate power, that is power being generated, and not just power loss in this case. Okay, another thing we can work out is obviously how much energy is used over a period of time. So we know that potential difference is the work to move a charge. Now we also know that a charge is derived from the equation that a current is just how many charges are going through the circuit over a period of time. So if I substitute charge, that IQ, into this equation here, I get that the potential difference is equal to work done divided by current times time. Now if I change that around, so I'm making the work as the main focus of the equation, I can say that the potential difference times current times time is equal to work done. Now we know that work done is just the change in energy, and we know that potential difference times time, that can be the equation we talked about before of power. So we can say that the change in energy is equal to power times time. So when we say power, it's actually the rate in which energy is being used. So power and energy aren't actually the same thing. Energy is the ability to do work, so that is to make things move. Power is how fast the energy is being used up. So that's the difference we have there. Okay, so let's go through a couple of calculation questions. Here we are trying to find the potential difference across a heater element. So that's the energy that's being used. And also we have a current flow of 5 amps and we have a time period of 30 seconds. Okay, so what we can recall is that energy divided by time is equal to power, and power is equal to potential difference times current. So what I'm going to do is to make V the subject, or actually substitute your values in first. So we have 3.6 10 to the power 4 divided by 30 seconds, our voltage times our current, which is 5. Move this value over, so times that on both sides, be 3.6 times 10 to the power 4 times 5 divided by 30 seconds. And that should yield you a potential difference of 240 volts. The next one we have is what is the power rating for this current and for this specific voltage. So the power rating would just be using the power formula, and that would be substituting 240 times 5 there, which yields us 1200 watts, which is the units that we're using to measure power. Alright, we can also work backwards to find this particular equation here. So we know that power is given as change in energy over time. We know that work done that we showed before, the work to move an electric circuit is given by this formula here. Remember, because we said that potential difference is work of charge, and then we said that potential difference is current and time, and so that's where we got this formula from here. Okay, so if we rearrange the equation around, knowing that work done, or knowing work done in this case is, if we rearrange the equation over here, so work done is the same thing as power times time. So we get that work done is change in time equals to voltage times current times change in time again. Okay. Power, sorry. So if we move the time in this case to the other side, we get this particular formula here. So the two times cancel out and we're stuck with this formula here. So that's how we can work one way to get one formula, or the other way to get this formula here as well. So these are the two major formulas you need to remember. So energy is equal to power times time, and then power is equal to voltage times current. Just remember, power is in watts, energy in joules. Alright, so let's go through the last two questions. It says how much energy is applied to a mobile phone battery rated at this particular voltage at this particular amplitude or ampere. Now the symbol MAH, so MA means milliamps, H means hours. The question is asking how much energy we've used up, so energy is what we're trying to find. Now, in a way, you can sort of think of this as the power rating as well. So we know that energy is equal to power times time. Now we don't know the actual power because there's no watts, as you can see. What we can do instead though is have it as voltage times current times time. The voltage we already know, it's 3.7. The current we already know, that's 1210 to the power minus 3, because that's converting milli into actual amps. And the time we're using is 1 for 1 hour here. Notice I haven't even bothered trying to convert this into seconds, because it doesn't really matter. If we're talking about this in terms of time, we can just leave it as hours here. So the value I get at the end, or actually, before I go through that, let's actually make this into seconds, because as we said, we measured time. We did say the SI units is in seconds. So in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds. So overall, 3,600 seconds have passed, so that's the overall multiplication we're doing, and that gives us approximately 16,000 joules of energy that's been used up. Okay, so that's there. Alright, and what we have as the final question, we have a toaster. You can even look at your own toaster to see what the energy rating is. We want to find the overall current. So the overall current is given as power divided by voltage. Okay, so it would be 700 divided by 240. That gives us approximately 3.125 amps. What is the resistance of our circuit? So we're using Ohm's Law here. We are going to do voltage divided by resistance. Oh, we're trying to find resistance, sorry. So resistance is equal to voltage divided by current. So 240 divided by 3.125. And so that is approximately 76.8 ohms. The last one we're saying is how many hours would it take to use up 35 kilowatts per hour. So kilowatts is 10 to the power 3 watts. This question is asking us about hours, so unlike the previous question, we don't have to convert it into seconds. We know that energy is given as power times time. So the power we've used up is 30,000. The energy we've ended up using in this case is 750. So the time, or in terms of hours of taken, to use this particular amount of power is 750. Divide that by 3,000 or so here. Okay, so the last one is how many hours would it take to use up 35 kilowatts of energy in that particular hour. So you can see the reason why I said energy, remember energy is power times time. Here we have the units for power. Here we have the units for time. So we know that this is a measurement of energy. The value above here is the measurement of power. Because it's asking us to measure this in hours, we won't be converting time into seconds like before. So we have energy is so just to rearrange, or actually let's just substitute all the values in. 35,000 into watts equals to 750 watts times the time. That's the hours we need, and so this is what we have. That is going to approximately equal about 46.66 repeater hours. Okay, so that's the amount of energy, or amount of hours to use up that amount of energy. Alright, so that concludes this lesson here. Quite a long one. We've gone through quite a bit of different content, but same as always, hopefully you found this video really helpful. If there's anything you're not sure about, please again just rewind and rewatch. Thank you so much again for the patience to watch these videos. I hope you have found them useful to your understanding of this module and physics overall. Until next time, have a good day and enjoy.